Okay, so what we've done so far is we've been storing charge and energy on capacitors. Like here's a plate of metal, here's a plate of metal, and I put some kind of voltage source here. And I get energy stored in there. I get charge stored over here, like positive charge over here, negative charge over here. That creates an electric field between these two plates. Now current isn't flowing, and we don't want current to flow right now. I think current flowing is next chapter. Okay, but this is our situation. Now think about a real capacitor in the real world, not just drawn on paper. It's simply a little piece of foil and another little piece of foil with a voltage, with wires connected to them. Now, what could go wrong when you have when you got a piece of metal here and a piece of metal here? What could go wrong? What could make this whole thing fail? A short circuit, or one of the plates touches the other plate, or you mush it. You drop your cell phone, bam, the two plates connect, and smoke comes out of your cell phone, and you've broke it. All right. So what we need to do is we need to keep these plates separate. And what we do is we put, basically it's gunk. Think of it as gunk. We're just going to put some gunk between the plates. No, it's not called gunk. It's called a dielectric. If I could spell it, it's spelled right above. See, dielectric. Now, what is a dielectric? It's gunk you put between the plates of a capacitor, and it serves several functions. One of the main functions it does is that it keeps the plates from touching each other. And this material, by the way, obviously it has to be a non-conducting material. Okay? Now, in your book, there is a table of different materials that we use to put between the plates of a capacitor, and they are called dielectric materials. There's a table. Here it is in your book. Okay. So air. Okay. Air isn't much of a dielectric, but bakelite. That's one of the early plastics. One of the first plastics made was called bakelite. Fused quartz, mylar, neoprene, nylon paper, paraffin, polystyrene, polyvinyl chloride, porcelain, Pyrex glass, silicone oil. They use that in cylindrical. It's a fluid. Teflon, vacuum, and they can even use water. Okay, now water, you got to make sure it's deionized water. It doesn't have ions in it, or it's not going to work. But so anyway, there's lots of materials, and there's lots of other materials too. I mean, there's people that figure out what you should use. Now, here's what a dielectric does for you as well as keep the plates separated. They actually increase the capacitance. Capacitance. The gunk you put between the plates will increase the capacitance of your capacitor. It'll increase the maximum voltage that you can put across that plate. Look, if you just had a vacuum in there and you put enough voltage across here, eventually the electrons are going to be able to leap off of the metal and go to the other side. And that's technically called a spark. Okay? A little electric spark. And you don't want that in your circuit. That's bad. So a dielectric material will keep that from happening, or at least you'll need a really big voltage to make that happen. Much bigger than you probably will ever get to. So it also, obviously, it keeps the plates from touching. Am I still on screen there? Nope, went off screen a little bit. Okay, keeps the plates from touching. So that's, and they call it a dielectric. I don't know where that vocabulary came from. I just like to call it gunk. Okay, you put the stuff between the plates, and it keeps the plates from touching. Now let's figure out why this actually increases your capacitance. And now the amount it increases your capacitance, it depends on the material. And what it does, what I'm going to do is I'm going to call it C naught. I'm going to start off with C naught. Now what is C naught? C naught is the capacitance with no dielectric. Now what that means is that you basically have air, or not air, a vacuum between your plates. It turns out that air behaves very, very closely to a vacuum. It's like, what capacitance are you starting off with? Now, if you put some gunk in there, it turns out that increases the capacitance by a certain factor. And we call that the dielectric constant. So if I put some gunk in there, my actual capacitance is going to be some little constant times C naught. Now this is, we use a Greek letter for this. This is a kappa, I believe. But actually what it's representing is something called the dielectric constant. And the dielectric constant, again, it just multiplies the capacitance by a certain factor, depending on what the material is. And it's in the table in your book. Look right here. The dielectric constant for paper. Let's just put plain old paper between the plates. It increases your capacitance by a factor of 3.7. 3.7 times the capacitance. That means I'm going to get 3.7 times more charge on my capacitor for a given voltage across the plates. That's a lot. But it's not a super a lot, because what you really want to do, look at strontium titanate, multiplies the capacitance by 233. That's good stuff right there. Okay, now why does gunk between the plates, why does it increase your capacitance? Well, because here's what it does. Okay, here's my plate. Okay, here's my two plates drawn in cross section. Now let's put a certain amount of charge on here. And this is the amount of charge that you, that you get. This is, from C naught. Okay. Now I'm going to put some gunk in here. Now I'm going to show it. I'm going to have a little gap, just for the purposes of my drawing, between the gunk and the plate. But it would actually be right up against the plate. So let's put some gunk in there. Now, here's what a dielectric or non-conducting material does. Okay, it does not allow electrons to flow. These atoms hold on to all of their electrons, even the valence electrons, right? Unlike a metal, right? What does a metal do? Those valence electrons, they're very promiscuous. They just go all over the metal, whatever atom they feel like, okay? But these non-conducting, can you get that for me, Tillman? So here's what it does. It